Okay, so it's a pleasure to have Andrew Hanlon from Study Group, and he will talk about monomial admissibility for Looijenga pairs. Okay.
Okay. Thank you very much. Yeah, it's a pleasure to be giving this talk, and thanks to the organizers for making such a nice conference. Unfortunately, I haven't been able to attend that many talks just because of the time zone and a very long and complicated move, but that's another story. So if there are any like technical issues, if you don't see my screen sharing or like you don't hear me or anything, please interrupt me. Or just if you have questions, don't hesitate to interrupt me. So I'm going to talk about this monomial admissibility story for Looijenga pairs. This is joint work with Abby Ward that we've been promising to finish like for quite some time, but it should appear. And okay, so let's get to it then. So I just give a brief outline here. I'm not sure how useful this is because it won't stay up, but so just so you have a roadmap of where we're going. So I'm going to talk a little bit about like the tropical and SYZ setup. I'm sure some of this was discussed last week and in various other talks, but I just want to make sure that I have the notation and maybe the point of view that I need to set this up. And then I'm going to talk about kind of the reason for doing this monomial admissible setup, the philosophy, and like how to start defining it. And then maybe more into the results section, I'll actually tell you like the key technical ingredient to define a monomial admissible Fukaya category mirror to Looijenga pair. I'll tell you about the objects that are mirrors, the line bundles, and some like first computations with them. And so the goal of this is to kind of set up the Fukaya category that I would argue should be viewed as the mirror to a Looijenga pair in general. And we don't have the full HMS story for this, but I'll talk a little bit about how it relates to what's known and what we can do. Okay, so let's start with the SYZ input. So what I want to study is homological mirror symmetry when I take on the B side a Looijenga pair YD. So I just hopefully from this conference it's clear what it is, but just so Y is I'll take a smooth rational surface with a singular nodal divisor that's anti-canonical. So okay, so from this data YD, Gross Hacking Keel produced the affine manifold with a single singularity that should be kind of viewed as maybe I should put this in quotes, as a degenerate SYZ base for the complement of D. So it's kind of like the SYZ base zoomed out infinity. And okay, and what can you do with this to get something that should be more like an honest SYZ base? Well, for every Looijenga pair, you can fit it in a diagram as follows. So you can take your favorite pair YD, you can take one map to another pair. So this map pi1 is this is okay, let me just write it first. And okay, so this first map pi1 is a blow up at some corner. So take something like this and blow it up to something like that. So this is a corner blow up, and the map, sorry, I wrote pi1 for this because this should be pi2, and this map pi2 is a blow up in some component. So I take this and I blow up at some interior point, and I replace D with its transform. So now I have some exceptional locus going through here. Okay, and the key point is that this Y bar D bar this is a toric Looijenga pair. So Y bar is the toric surface and D bar is its toric boundary. Okay, so maybe just to have one concrete example. For instance, if I took, I don't know, P1 cross P1, which is one of my favorite surfaces, and I took the anti-canonical divisor that was two of the lines and one smooth component, like that, then if I do one blow up, if you blow up at this corner, then you can realize that the resulting pair, the total space, is now a blow up at 2 points of P2. And of course, the boundary looks like this. So let me label them by their intersection numbers now. So this is 0, -1, -1, 1. So this -1. So is the one that we added. So sorry. So these ones are 0, 0, and 1. Sorry, let me just do that. And if I blow down this thing, and now you can find some exceptional curve that's transverse to this, and you can blow down to get back to the toric blow up at a point of P2 that looks like this. Okay. And okay, so so when we, as other people have done, when you have realized, when you choose such a toric roof, is what I'm going to call this data, then this allows you to modify the base. Okay, so that allows you to modify this GHK base. Maybe I should have written this like this, into the base of putative SYZ fibration and YD. And in some cases, like this SYZ fibration is honestly you can actually honestly find even a special Lagrangian fibration. Or okay, so I'll say that if you want to look about, like, if you actually care about producing SYZ vibrations, I think that you should compare with this work of Collins, Jacob, and Lin. Okay, so so let me explain how you resolve this base. So okay, well, when you take a toric roof, so we had these two operations. So we had pi2 and pi1. So I'm going to view it in the opposite thing, that I start with the toric thing, and then I do some operations to get the base for the Looijenga pair. So for pi2, what you're going to do is add a slit, and I'll draw a picture of see what this means. Parallel. So let me say to some ray rho, which corresponds to the divisor. So since you started with a toric thing, you're blowing up in some component of d bar, and that corresponds to a ray of the fan in the interior of the star of rho, with a height that depends on where the blow up is. I won't be too specific about that for now, but and in terms of actually producing an affine base of singularities, this is actually all you need. But I'm gonna carry around a little bit more data, and I'm gonna keep this like picture of the fan from the toric thing hanging around, except whenever I do one of these corner blowdowns, when I blow down a component of the divisor, so I do pi1, I'm going to remove the ray rho corresponding, let me say, the ray rho that corresponds to my divisor component rho. Okay, so so let's do an example just to make this clear. So I start with, so if I go back to this example that I had here, I start with the blow up at a point of P2. So I have my toric picture that looks like this. I'll draw it in the same thing that I did. So then first I'm going to look at this operation, which was so now I want to blow up on this component here. So what I'm going to do is add a slit to the affine structure somewhere in the star of this ray. So I can put it like this. Okay. So now this is so now what this slit means is that I've drawn this affine manifold as embedded in R2 up to the complement of a line, and when I cross this line, the affine structure changes by the shear that fixes this line. So this is like 1 minus 1, 0, 1. Okay, and you can and then in this case where I blew back down the same thing, this is a simple case, I guess, but I remove that ray and I keep this slit. Okay. So, and for a more complicated, I mean, I can do this like however you want. For instance, I mean, okay, now maybe another example, start with the P1 cross P1, and you can do more blowups. So I don't know, say in this case that I could do 2 blowups to the same point so that they're lined up on this point over here. So they're lined up like this, and maybe 1 over here, and I'll just keep it lined up with the array like that. And then I can blow down this. One of these has self-intersection number -1, this one to the left, this one, and I can blow that down and get some Looijenga pair. This would be the diagram that I remember. Okay, and the fact of Symington that has been known to experts for a while and used by Hacking Keating, for instance, is that the output of this procedure, so even from the pi2 procedure, which I'll call B, determines a unique symplectic manifold that has a Lagrangian torus vibration over this B with singular fibers sitting above the singular points. So, and as such, if you believe that this comes from some SYZ type vibration on Y, then this allows you to produce essentially for free from this data what the mirror to Y minus D should be as a symplectic manifold. Okay, and now the main topic that I want to discuss is what do you do with this extra data, this fan that's lying around, and how to think about it as a mirror to Y. So I guess I should also say here that plus I can construct M. You can take a Lagrangian 0 section, L0 in M. So you can fix some Lagrangian section such that reference over this thing such that in all the true affine charts, it looks like the 0 section of the cotangent bundle. Okay, so now to the, again, if there are any questions, please just stop me. But so now to the monomially admissible philosophy and how I would like to argue for thinking about what the compactification does on the A side. Okay, well, the law, I mean, this is nothing new, but what we generally think of in this log collab EL type story and mirror symmetry is when we're working in this direction is that the compactification of Y minus D to Y you should think still about Lagrangians in the mirror to Y minus D in this M, but you should put some boundary constraint on them. So what the monomially admissible point of view is to do this and like keep the SYZ philosophy at the forefront and just follow what that should say. Okay, well, as we've seen, the fan of the toric model or the toric thing that we put in this roof persists to a fan sigma in B. What I mean by that is like I just take like I still have these rays which are actually affine invariant because every ray was like these are affine submanifolds because every ray was parallel to any kind of slits that I added in the region where it is. And I remember just like this collection of rays that are left over after doing these operations, and some cones between them. Okay, and what you should think is that, well, the story, so the story is that what these rays are there for from the SYZ perspective is they tell you which directions at infinity you go where the SYZ fiber, where portions of the SYZ fibers collapse. So just to do, so for example, in a toric P2, if I draw the fan like this, so I have these rays, what this tells me is that if I go off to infinity in any direction like this, then over all these points, so if I go parallel to this ray in its star off to infinity, then over all these points I have a torus, and they limit actually to some circle that sits in the divisor at that point. But if I went off in one of these cones in direction not parallel to the ray, but actually strictly in the convex hull, if I went along some line like this, then my tori here collapse just to the intersection point of the two divisors. And so, I mean, this is one well-known way from toric geometry to construct the fan, is to take the limit points of one parameter subgroups.
I have two questions, Andrew. May I ask? So the first one is maybe a philosophical question. So you're starting with Y, D in the B side, and then you construct some symplectic manifold.
Yes.
But if the Y minus, so of course you should get Y as a mirror again, or Y minus D as a mirror of what from the symplectic one, but something is wrong with the, or something is missing from the parameters, right? So the Y comma D has model I. Your M also has model I, but they are real at the moment. How do you match these model I?
So yeah, I mean, of course, if you wanted to be actually careful about doing it with the moduli, I should put some kind of B field probably on the symplectic manifold. Yeah,
but you have choices, right? I mean, so I mean, you're starting from a GHK picture, which kind of is, and then kind of move away the singularities from the origin, which is kind of taking the historical perspective around, because that's what Mark and I had done before. So, but if you take the picture that I had with Mark in like 2007 or so, you would have already the singularities away from the origin, and there would be an honest symplectic mirror. I mean, it has both informations, and we match the model I. Now you're saying you kind of take this kind of collapse picture, moves the singularities away in kind of unspecified ways, even allowing them to kind of move in changing the radiance obstruction, which changes the model I, as we know, and then produce a symplectic manifold. So this seems, so I'm a bit lost in that.
I think sorry, I mean, probably the order, and I think what you're getting at is probably the order in which I'm saying things is actually not so, maybe not so accurate. So you should probably think more that I just start with the picture where the slits are already pushed off. I mean, I was just trying to, I guess I'm just trying to say that, like, in some sense, if you just want to see like the whole moduli space, that like this original, like this like GHK collapse base, I mean, in some sense knows like all the monodromy infinity. And then if you want to refine like the actual moduli in CYD, you need to understand like how to push off the slit. So I was being a little bit vague. Or if you want to think about it more from like your and Mark's perspective, maybe you already take a base where the slits are pushed off, and then you match it up with the with the
right.
mirror
I
space.
think it's not unique. That's the point, right? So starting with the kind of affine information you get from this collapse picture, that's not enough, right? So the GHK perspective really starts from the Y comma D, and then you get a unique mirror, but that is really the Y comma D is really the symplectic side. And then you construct the complex mirror. But what now you want to do it the other way around, and then I think it makes more sense to really already have the kind of move the singularities out from the origin to have an honest kind of complex base at the point where you know what the mirror is, a symplectic mirror, and then do something. But yeah, okay.
Yeah. I agree with you. I think that I'm just explained it in a confusing way. Yeah, I want to.
Yep.
I think you can just forget about like the degenerated base and just start with the base where I have the slits pushed out in some direction.
I'm just wondering why it would work. Start with the degenerate one where you have a very precise picture already without degeneration. Anyway, so the other question is, now you're drawing what looks like a momentum polytope picture into a fan with these. That seems to be on the wrong side. It's an SYZ base. Okay, so that's a momentum polytope, but then you don't have collapse of circles, right? And this is just not a non-compact base.
Yeah, it's a non-compact base. They don't actually collapse. It's just there is like this. So I'm specifically trying to not draw the moment polytope because I want to think about this YD entirely on the B side. So here I'm drawing the fan, and I'm pictorially representing something that looks like if I had added in a boundary to infinity, but this is really, here I'm taking a limit on a one parameter subgroup. So
that's on the Y side, not on the M side?
This is on the Y side. Yeah.
Oh, okay.
Yeah. This is not in M yet. Nothing is in M yet. I'm just so far I'm talking about what happens on Y. So that's like
but then
up to here.
And then the straight lines should be in the momentum polytope. That's dual. If you want to write down these kind of fibers, these torus fibers, or maybe it's not straight. You just want. Anyway, maybe you continue. I kind of disagree with the picture, but maybe you have a different way to think about it.
So I guess let me just, what I would quickly say to that is just like, if I'm thinking about, say, let's just say in this toric P2 case, I would think about this as the SY, like the B SYZ fibration on P2 minus D, not the A SYZ fibration.
But then what's the origin? What is the origin? There's no distinguished thing there, right? The P2 minus D is just C star squared. That's an R2.
Yes.
And the action of the torus moves the origin, right?
Yes.
So why? And what is this kind of fan of P2 that you drew in this picture? I don't understand.
This is identifying if I think about the torus in P2, it's like I can identify it with like N tensor C star, yeah. And I take the log map on that, and that naturally maps to N tensor R, and the fan lives there. And the components of the fan can be viewed as like where, if you take which points converge to the different toric fixed points of the strata.
I disagree. The fan lives in the dual lattice. It's not N. It would be. I mean, if your torus is N tensor C star, the fan lives in M tensors in M, right? Or M tensor R. It's a dual lattice. I mean, there must be some kind of identification of dual things. Maybe you have a metric in the background or something. The fan
important point.
Don't live in dual spaces, right? I think we agree on that.
the fan and the polytope are in dual spaces.
Yeah. So this seems to be
but the
same.
torus that sits inside of the toric variety is n tensor C star, where the fan lives in n tensor R.
Ah, that is true.
Yeah. So if I take the log map on the torus that sits inside of the toric variety, this is a map from n tensor C star to n tensor R, which is where the fan lives. And if I look at one parameter subgroups inside of there, they look like, I mean, okay, here I drew one that's shifted off, but if I drew the one that's like along the ray, they look like straight lines. And they record like which points converge to the components of the boundary.
Yeah, I think something is wrong. I mean, the log map is a momentum map, but anyway, maybe I don't want to destroy your talk. Maybe you just continue.
Okay. I think the issue is maybe we mean different things by log map, but okay. Anyway, maybe we discuss it afterwards. Yeah. Okay. Okay. So. Okay, maybe I'll apparently this is a very confusing point, but maybe I'll continue anyway. So the point is that if you think about this fan as sort of recording degenerations at infinity, then from the SYZ perspective, what should happen is that you should have the dual tori to the dual subtori to these circles, which are again just circles in this dimension, should have to be constant along these circles, or they need to, from the SYZ perspective, they need to limit to a constant. But from the Fukai category perspective, it's simpler to just require it to already be constant. So here's what you can do. So you have this remaining fan in the base. So you have this fan in the base. And what you can do is for each ray, you have a vector field over the star of that ray, which is just defined by parallel transporting it. So at near infinity, and by near infinity, I just mean outside of some compact set. I just take some big compact. So I need to say what to do with Lagrangians outside of some large compact set, so I can pick one. So the picture here is, say that I had some piece of the fan that looks like this. And here, maybe I should be consistent and draw that in black. Then, and here I had added some slits that looked like this. Maybe there's one like this and whatever. So now I can take some big compact subset here that contains all of this. And then this piece, the piece that's left over in the star, is some simply connected affine submanifold. So I can trivialize the affine structure, which means, or in other words, I can just take, so I take this vector, the primitive vector parallel to this ray, and I can transport it to a vector field over this whole region. And maybe over, if there are some slits from the nearby rays that got pushed in, it gets twisted a little bit, but it doesn't in this picture. But it doesn't matter so much. Okay, and then what I also do is then I'm going to choose a closed cover of B, this delta. This is what I would call a monomial division. And what I do in the picture then is, so I choose one for each row. And what you should think about this as being is just okay, you have to make some like actual choice. It doesn't matter, but I should think that I took this picture with the slits and everything, and I choose some essentially region corresponding to this ray that looks something like, maybe I just rotated the nearby rays in a little bit and took like kind of a conical picture. So this would be, for this row, this would be like what my C row looks like, and these cover the space. Okay. And now, to translate what this condition was, like what the mirror to these collapsing tori is I would say the Lagrangian is monomially admissible if for each ray in this leftover fan, I have that in my C row outside of a compact set where this V row makes sense, theta of V row is 0. Now let me explain what that means. So what this theta is, okay, well, near infinity, the portion of M over C row can be identified with T star of C row mod a lattice. And here I have coordinates now B theta. And what I'm saying is I just pair the angular coordinate with this vector field. That makes sense because this vector field is in the lattice. And this is being 0 as an element of R mod Z. So really I'm asking for this angle to be just some multiple, some integral multiple, or if you prefer to think about it more as an angular parameter, you could think of it as 2 pi Z. Okay. So that's what a monomial admissible Lagrangian is. And so in the toric case, what this is saying is just that that I take if I take like some ray in the fan, I'm just taking the argument of Z to the alpha or Z to the U row, where U row is the generator, that this is a multiple of 2 pi along my Lagrangian infinity. Okay, so maybe just I added this slide just to try to keep track of where we were. So I should think that whatever I had this Looijenga pair with a toric roof, and that this can be, as Bernd was saying, can be captured by some kind of tropicalization, and that from the symplectic perspective, basically all you need. So you need to just remember that can work entirely with, and this work entirely here, where you have this kind of tropicalized picture and this reconstructed symplectic manifold with some kind of this monomial division, which dictates the behavior of Lagrangians at infinity. Okay. So that's where we were. Okay, so maybe I'll go more quickly over that than I planned. Okay, so now this is where this monomial admissible thing maybe buys you something. I'll try to explain how. So now you have this Fukaya category, or you don't have a Fukaya category yet. You have these Lagrangians in this non-compact symplectic manifold M that have some boundary constraint in infinity, and you want to know why does this give some kind of well-defined Fukaya category? Well, the point here is that, yeah.
So, I mean, isn't there even a proof in Hanlon that the mirror to Y is some kind of Lefschetz vibration? So it's like
yes. So
defining stuff.
Yeah. So I guess maybe I should have said that one first, but I was going to get to that in the next slide. So the point. So in Hanlon, you take this distinguished point in the moduli space. It's an exact. Corresponds to M being exact, yeah, and you produce a mirror to YD at that point that comes as a Lefschetz vibration. Well, so from that perspective, I mean, one, it's hard to see what you would do in a non-exact case, and it makes like, I mean, and you kind of lose a lot of the information from this whole tropical SYZ vibration story that you don't have like immediately. I mean, they do a good amount of work to relate it back to this vibration over YD and what the Lagrangian should look like with respect to that. Well, whereas here, what I'm trying to do is set up a Fukaya category where, well, one, it makes sense without this exactness assumption, and two, that the XYZ fibration is like already apparent, and the Lagrangians that you're going to consider are already look like sections. So that it does things like make certain functors, like, I mean, which Hacking and Keating have also been able to do, but through a bit more work, it makes certain things like functors like tensor product between line bundles like almost immediate once you've set this up. I don't know, does that answer your question or not?
So I see in the not exact case, you're saying this is some kind of some notion that generalizes the stopped.
Yes.
Stopped partially wrapped category.
Yeah, in this setting, yes.
May I ask a follow-up question on that? So does the exact case, so I was wondering about these non-radiant deformations of your singularities of the affine structure. Is that related to exactness? So is the exact case exactly the radiant F structures?
Yes.
Ah, okay. Ah, very good. Thanks.
Yep. Okay. So yeah, so yeah, I'll say a little bit more about that on the next slide maybe, but just to try to explain what's going on here. Well, okay, what one can do to get to prevent holomorphic disk escaping from this setup is that you can take what you're going to do is apply a maximum principle to the maximum of some functions which are locally holomorphic. So morally, you should be thinking that these W rho are like come from some discounting potential on the mirror on Y if I had chosen some symplectic structure on Y and done a lot more work. But the point here is that to define the Fukaya category, you don't act like, as in the exact case where you can just produce this Lefschetz vibration, you don't actually need to do all that. So let me try to explain a bit. So what I want to look for are functions that kind of mimic these. So the key thing, the first key thing is just that the argument of each of these W rho is theta V rho in the region that so I guess I should say like this should be like actually like pi inverse of C rho, where I have pi is my map from M to B. But and all of this is again happening outside of a compact set. So this V rho still can make sense there. Okay, and then the key property for this to work. So this is like, so this first, okay, so maybe let me say a little bit more about the first one. The first one is saying something like from the function W rho, where in C rho, that my Lagrangians project to just like the real positive axis on our W rho. So it looks kind of like locally what you would do with a superpotential, but you just do it piece by piece. Okay, then the second thing is, in some sense, like sort of that this W rho, this collection W rho tropicalizes appropriately. So if I took the norm of W rho at a point X, again, this should be pi inverse, then the maximum over the rho is achieved by a rho such that X is there. So that tells me that sorry, I'm losing battery on my computer here. Let me try to plug it in. Okay, I might need to rotate my setups. Okay, I apologize. That was not smart. Okay. Okay, so so that's kind of like this in some sense. This is a bit tricky. I mean, so if you took the functions to actually be some kind of discounting potentials, then this 0.2 can be kind of tricky because you need to have chosen like the correct Kähler structures and matched up both things. Okay, and then the last point is just that these W row are kind of locally holomorphic for some not necessarily integrable, almost complex structure. So the key point of like taking this approach is that, as I've been trying to say, is that you can choose these functions W row. So so you don't actually have to do any discounting on the mirror. You can just kind of use the SIZ base I can convey, and this lemma that they exist, this is sort of in a sense done locally. So you define W row in it and its neighboring ones in local charts, and you kind of, when you're not in the overlap, you can kind of patch together from one to the other. And once you've done this, then when you apply the maximum principle, you can show that disks are the holomorphic disk can't escape to infinity, and you get a well-defined Fukaya category associated with this data, which using essentially standard techniques. Okay, so then one can make some kind of homological mirror symmetry type statement that you would expect, which is like essentially the long-term goal of setting this up, which is that there's not that if I've been more careful, as Baron pointed out, about matching up the moduli, and I've added a B field, then the Fukaya category, this monomially admissible Fukaya category, this F delta M, is quasi-equivalent to sheaves on Y. And as Umit already pointed out, for the distinguished point in the moduli space, where M is exact, a version of this statement has already been proven by Hacking Keating, and one could hope to relate. So F delta of M is maybe closer. So in this setting, is closer to a partially wrapped category. Which is like stopped at a certain combinatorially defined stop. And which, I mean, so I think that this stop is for instance, appears is hinted at in the work of Gamage and Lay, and you should be able to relate this. In that case, probably the easiest way to go from the monomially admissible category to the Lefschetz category, where Hacking Keating work, is to go via the partially wrapped thing and then show that is like some relative skeleton for their Lefschetz vibration. Okay, so now I want to say a little bit about if you wanted to work directly in this monomially admissible type setting, what you can do to start constructing some Lagrangians, maybe trying to compute morphisms between them.
So your Fukaya category from the previous slide, is it over C or is it over the monomial field?
Yeah. So okay, so yeah, I should have made a comment about this. So yeah, I don't know. So this Fukaya category is now a priori only defined over the Novikov field. If you were a bit more ambitious, you would maybe want to try to do this over C. But in the exact case, of course, it's defined over C. In the non-exact case, I don't know any reason how to show that it's defined over C.
But how about Y then? What is Y?
Yeah. So then in this case, I have this Y that's defined over C, and I should do some base change to get over the Novikov field. And then I need to be a little bit more careful though.
But it's not
what's the pro?
Is it a degeneration then over the Hanlon field though, or will it be just the base change?
No, it shouldn't. There shouldn't be a C model if you're really defining things over the Novikov field in the radiant case, like not when the radiance is not zero. It shouldn't be just defined. It should have a C model. You can prove convergence and maybe get something. Okay.
Yeah. I guess that's what. Sorry. Maybe I'm being a little bit sloppy here. So maybe for now, maybe I just leave it as like, I don't like, as Uma says, I think that you can like, what you would want to try to prove is some kind of convergence result instead of just like it being straight defined over C in the non line, in the case where it's not lined up. But okay. Okay, so of course, like it goes back a long time in the Gross-Seibert program that line bundles on this Y are also recorded by this sort of tropical data. So one way to do this in this setting is so for now I'm just gonna assume that all slits that have been pushed off so that they're not on the radial direction are parallel to array of sigma. So this is just a simplifying assumption for what I'm going to say. You could say a few more words to get the general case. So this is just some. And okay, so what I mean by this is I'm not like, so if I did something like, I'm not allowing something like this, where this ray would have been here, but now it's not. So that's not allowed. Okay. Okay, so now I'm going to produce a graph on the base as follows. So what I'm going to do is I'm going to draw, so you just draw sigma 1, so draw all the rays of the fan, and then from each slit parallel to a ray, if it's not already there, or just like consider it as, so I draw the invariant line going outward, and for each slit which is not parallel to a ray, and of course, so in this case it would have had to been lined up with the origin by my assumption. You draw a line from the origin to the start, the singular point. So, for example, if I had a diagram like this, maybe I should do like this. Let's do the example like this. Maybe I have something like this. I would draw a graph that looks like, I wanted this one here, that looks like this. So I would start by drawing just these, and then for these two that do correspond to rays, I would just draw those, and here I would draw like, here I would just draw like this. So here's my graph gamma in this example. Okay, and a definition of gross, that this is like some maybe slightly degenerate setup of it, is that the sheaf of what he would, I'm just going to simplify the tropical differentials call it, but he would call multi-valued piecewise linear functions on this setup is the quotient sheaf of piecewise linear functions with respect to this graph gamma by affine functions. So piecewise linear affine functions by genuine affine functions. So what this reduces to in this picture is, so this is the data of linear functions, of PL functions on the following regions. So if I copy over maybe this picture, then I have some piecewise. Then I have like this whole big region. I have these three regions. I have PL function in these regions that agree up to an affine function on overlaps. Okay. So here, well, okay, so maybe I'll skip, maybe I'll do these slides in the opposite order because of time. But so here's the statement is that, okay, so this is, so the first statement is basically like implicit in the Gross-Seibert, or like, sorry, appears in the Gross-Seibert program and is essentially implicit in GHK, is that up to that the Picard group of Y corresponds to these tropical differentials, and that and then the Hamiltonian isotopy class and these also correspond to Hamiltonian isotopy class of monomially admissible Lagrangian sections. So the idea is that because of the piecewise linear behavior with respect to gamma, so let me just say something about how this last step goes. So you produce a section by appropriately smoothing df, where I think about f as being this section of this sheaf, and the fact that they differ by a linear function means that like the section that I take in the Lagrange, like that takes df makes sense, and the PL nature with respect to gamma allows one to do this so that they are monomially admissible. And this is essentially like in some sense a natural thing to do. Okay, so I have here an example of what in one case where you're in like the exact setting of what these things look like. So here I've drawn some functions where U1 and U2 here are coordinates on R2, this is some Looijenga pair who has a toric model, which is the P1 cross P1, which I did some. So I started with P1 cross P1. I did some interior blow-ups, and then one blow down. So here what I'm calling D1, so this is my D1, D2, D3. And what's recorded in these in this kind of tropical data, which persists when you take the isotopic class of sections in the lab allows you to
Andrew, your screen program.
Classify them.
Andrew, can you hear us?
Is the
Andrew, can you hear us or?
is
we don't see your screen.
what I would call the twisting number to cross
Poor guy.
these rays. So for instance, you can see like
Is it us? Are they other people? Are they here? Well,
you can see like how yeah. Do you hear me now?
Perfect.
Yeah, it was actually not a problem with the internet, but like my computer like freaked out with that slide and froze. So, okay, let me maybe, in some sense, I'm already out of time. Maybe instead of, what do you say?
we can have a little bit more, but we can't share. We can't see what you're sharing.
Yeah. I know. I turned off the share to resolve the issue. So, it wasn't the internet. It was like didn't like that slide for some reason. So, let me do the following. Let me try one more time, and if it doesn't like it, then let's do this. Let's try. Does it work?
Yes.
Yeah.
Okay. So, in the interest of time, let me just say that. Okay. So, maybe I'll just say it here. Is that the point is like that you can distinguish these by like looking at so there are overlap regions between the different regions where you're controlling the angles of the function, and on those overlaps your Lagrangian is essentially forced to be the zero section because both angles evaluate to zero and they're linearly independent. So if you want to start, so the idea of how this goes, if you want to start to recover the data of the section,
Andrew?
No, he doesn't hear.
Is you look at how it changes. I think I'm cutting out again. Yeah. Okay. Yeah, I think it had an issue again. Yeah. Do you hear me now?
Yeah, just end the story, and then you will post your slides online, and you can.
Yeah, that's fine. So so now I think it may be okay. Whatever. Okay, so yeah, I apologize. I never had that issue before, but okay. So maybe the point I wanted to just get across. Okay, now the next thing I'm going to say, which is going to be hard to do without doing a picture, is that you can for like a section that's supported on the boundary divisor and is ample. You can compute its sections by the integer points of a polytope, which is a result of Mandel, and in this setting you can directly see that also by taking some sort of Legendre transform with respect to the function. But maybe without slides, maybe I'll just stop here. I apologize for the technical difficulties. So the main point, in any case, the main point I wanted to get across is that from the SYZ perspective, it's natural to think about the terms of the superpotential as being distinct things, which you can define a Fukaya category of Lagrangians that behave with respect to those. And somehow, when you're working only with the pair Y on the B side, you're taking its symplectic mirror, that data is kind of all the data that you should have anyway. This is related to known construction, but sort of you can generalize it to the beyond the exact case. So okay, so I'll stop there. Thank you.
Okay. Yeah, that's thank Andrew. Okay, any question from this room? Okay.
No, I mean, I don't know. I can. So, can you, from this kind of new definition of Fukaya category that depends on extra data, not just the symplectic manifold, can you say something about Fukaya category of the underlying symplectic manifold? Like, is there any?
Yeah, I mean, so it should be like, well, so what you have in general, which I a little bit swept under the rug, is that now when you want to compute Hom between two Lagrangians in this category, then what you need to do is push like if you're taking Hom between L1 and L2, then what you do is push L2 like all the angles for L2 in each region a little bit. So you need some Hamilton, and to do this you need some Hamiltonian or really Lagrangian which gives you a Lagrangian that corresponds to the anti-canonical class in this setting. So when you have that, so that's that distinguishes what your kind of wrapping at infinity is, or partial wrapping. So once you have that, then you would want then the story is not really any different from the standard one. If you can compute the natural transformation that takes you from the identity to this wrapping functor that you're using to compute Homs with, then you can localize that and get to something that looks like the wrapped category of the total space, or a wrapped category. So, so in the exact case, in the exact case where everything is toric, some of my previous work I computed that and related it to the more standard wrapping. In the non-exact case, I don't really know what this, I mean, this gives you some kind of Hamiltonian where you would have a well-defined wrapped category where you'd expect to get the right answer, but it's not clear like what you should be comparing it to, I suppose.
So what you can prove is that the construction might depend on this choice of Hamiltonian. Like the category that you get at the end might depend.
Yeah, right. Yeah. I mean, I haven't really thought about it that much, but I don't see. I mean, there's going to be some choices in choosing the Hamiltonian. Those choices won't matter, but like, of course, like you could ask, like, if you did some kind of different behavior at infinity. I mean, it's kind of clear from the mirror symmetry point of view, this is what should be done, but yeah.
I have a question about like you, when you push these singularities off of the rays, you
Yes.
I guess the amount that you push them is something like the periods of the real part of the holomorphic two form. Yeah.
Yes.
It's like we should be taking the base with respect to the symplectic form, which is the real part of the holomorphic two form. So like how sort of encodes like the periods against the imaginary part of the holomorphic two form?
Yeah, you need to add a B field to get that.
So what's concretely look like in this situation?
Can I answer that, Andrew? Like,
sure.
Yeah. I mean, so the point is that like, if you're doing, I mean, you're exactly right, Phil, that like you're encoding these periods like with the push off or whatever. But like the most natural description, I think, is if you take these toric models and you think about like how the points are, like generally you blow up at like this distinguished point -1, but like if you blow up instead at like, you know, like -A or something, you want to push this corresponding slit off by like log A, if that makes sense, or log -A, I guess. Yeah.
Log of absolute value of A will be.
Yeah, exactly. Yeah.
But yeah, so what I was asking was like, what with the, if you consider the periods against the imaginary part of the holomorphic two form, like, I mean, shouldn't that somehow go into the definition of this category ultimately? It should. Like in terms of the structure constants of multiplication for the category, like to get an equivalence of categories, I think that.
I mean, probably Andrew could answer this just as well as I could, but yeah, I mean, you're going to need to also equip your underlying manifold with like a background, like with a B field, and then you want to consider, so you know, like a B field, which like as a cohomology class is just like in like H2, with coefficients in like R mod Z, but like really you should think about it as some sort of you lift that to an honest two form. And right, that'll factor into like your structure coefficients. Sorry, Andrew, I'll stop. Yeah.
So it's like, but it has to be like an actual two form, for instance, because like it should be integrating even against non-closed surfaces to be the right angle somehow.
Yeah, the formula for what the B field should be more complicated than formula. It's not just the real part or the other.
But it's actually not so complicated because you know that like you know what the deformations like in the real direction should be. So you can just like say like, okay, well, I'm going to consider, you know, a family of symplectic forms on my underlying manifold. And then you have some two forms there, you subtract off the exact symplectic form. And then you can just say, okay, like this two form should be in the right like cohomology class to produce for me my B field. So like actually you can just get the B fields by sort of by fucking around. Yeah.
It's like your own cohomology relative to the singular fibers or something. God, I don't know.
So I feel like I should stop answering Andrew's questions. So.
No, you're on a roll with this one. So
I mean, what do you mean the FL? You mean the B field on the B side or the A side? Or like, sorry. Like, yeah, the B field should encapsulate like the imaginary parts of the periods. I agree.
Cool, thanks.
Okay. Another question here? Or any question in Zoom room? Okay, let's thank Andrew again.